Hi students, this is AJ sir. Let's study 10th standard ICSE Physics chapter 12 section B, nuclear fission and nuclear fusion. Also, to enroll for my online lectures or online test series, email me. Check the description for more information. E is equal to mc squared. This is arguably the most popular equation in the world. Yes, it was propounded by Albert Einstein, and the meaning of this equation is that during a nuclear reaction there is a loss of mass because it is converted into energy. Now, that's a very simplistic way of putting in. There's a lot going on out here. But for 10th standard level, all we have to know is that during nuclear fission and nuclear fusion, matter is destroyed and converted into energy. That's not technically right, but that's how you'll remember it. So delta M is a loss in mass in kg. C is the speed of light in vacuum, which is the fastest thing in the universe. And E is the energy released in joule. Now, because C's value is so great, you can imagine that just 1 kg of mass can release such a huge quantity of energy. But this should be the loss in mass, not the actual mass of the substance. Now, if you look at this equation, you see that the uranium-235 atom was bombarded with a slow neutron. Uranium is already radioactive and unstable. It has a half-life. But as soon as it absorbs this low neutron, and yes, it should be slow so that it is absorbed, otherwise it will just bounce off, its atomic mass becomes 236, which is highly unstable, and spontaneously it will decay to give you smaller atoms. It will split into smaller atoms, that is barium, krypton, or some other combination, and it will release a few more particles like neutrons, highly energetic neutrons. This process is called nuclear fission, and in this process a lot of energy is released, because if you take the total mass of these products formed and the total mass of the reactants here, you will notice there is a loss in mass. Yes, the atomic number and the mass numbers are preserved. For example, atomic number is 92 plus 0, 92. And here too, 56 plus 36 plus 0 is 92. And even the mass number, it's 235 plus 1, 236 on the LHS. And even here, 144 plus 89 plus 3 into 1, that is 3, is totally 236. So the mass number and atomic number is preserved here, and yet when you actually weigh them, there is a slight loss in mass, but even that slight loss in mass is sufficient to generate a lot of energy in the form of electromagnetic waves, as well as in the form of the kinetic energy of these particles. And what we are interested in is the kinetic energy of the neutrons being released here. So here 3 neutrons are being released. If we can just slow them down and make them hit 3 more uranium atoms, then they will also split into simpler atoms, giving 3 neutrons each and releasing a lot of energy. And then those neutrons will hit more uranium atoms, and this is called a chain reaction. It's like a domino effect. And very soon the entire mass of uranium will undergo nuclear fission, and all the energy combined is so immense that it can be very destructive if not controlled. In fact, that is the principle behind atom bombs, an uncontrolled chain reaction. There are some other products possible as well. Apart from barium and krypton, we can even have lanthanum and bromine, or barium and krypton with different mass numbers. You see, atomic numbers are fixed, but the mass numbers are not fixed. They are simply isotopes. So these are some other examples which you need to study. Now note that even these products formed, barium and krypton, are usually unstable. So even they will decay further. Maybe they will give out beta particles and gamma rays, and that will keep on happening till they become stable atoms. Apart from uranium-235, we even have uranium-238 available in nature. In fact, that is way more abundant than uranium-235. But still, we prefer uranium-235 for nuclear fission compared to uranium-238 because we can bring about its fission even by using a slow neutron, which is easily producible. On the other hand, uranium-238 can undergo nuclear fission only by using fast neutrons. Now, the amount of energy released from this one atom of uranium is around 190 mega electron volt, that is MeV. That's a very small unit of energy, but that's just from one uranium atom. Imagine billions of such uranium atoms undergoing a fission at the same time. That would release a lot of energy. But we can use this energy for constructive purposes also. For example, in a nuclear power plant to produce electricity. Instead of using it for nuclear bomb, which is just another name for atom bomb, we should rather use it for producing a clean source of electricity. Now, how does that work? Now, this is how a nuclear power plant looks. In the nuclear reactor, we have the uranium rods, and we have cadmium rods in between. These cadmium rods will absorb the excess of neutrons. If you remember, from one uranium atom after fission, 3 neutrons can be released. That will help 3 more uranium atoms to undergo fission. That would produce 9 neutrons, and that will keep on multiplying. And that's an uncontrolled chain reaction. But in order to control it, we have cadmium rods which will absorb the excess of neutrons. Let's say out of 3 neutrons, 2 are absorbed and 1 goes on to hit another uranium atom, and that will release 3 neutrons, but again 2 are absorbed by the cadmium rods. So the third neutron will again hit another uranium atom. So now the chain reaction is controlled. Now the amount of energy released is less, and this energy will then be transferred through this hot gas to the heat exchanger, which will convert cold water into steam. And steam has a lot of kinetic energy. It will rotate the turbine, and the turbine is connected to the generator. And we know that whenever a coil, an armature coil, rotates in a magnetic field, electricity is induced. So that's how we produce electricity, using the energy released by nuclear fission of uranium. Now the graphite block and heavy water, they are used as moderators here. They slow down the speed of the neutron. You see, uranium-235 can undergo fission only if a slow neutron hits it. So what's the difference between a radioactive decay and nuclear fission? Well, radioactive decay is a spontaneous process whereas nuclear fission is not. This can happen at any time, it's not in our control at all. But this cannot occur by itself. It is initiated when neutrons are bombarded on a heavy nucleus. So it's instantaneous as soon as it is hit with a neutron, but it's not spontaneous. Here, alpha, beta, and gamma rays are released, whereas here the nucleus splits into two nearly equal fragments. So those products are formed like barium, krypton, neutron particles, etc. Here the rate cannot be controlled, the rate is fixed, but here the rate can be controlled. Now the next type of nuclear reaction is nuclear fusion, which is quite the opposite of nuclear fission. In nuclear fusion, two light elements combine to form a heavy element. Now even here there is a loss of mass. If you calculate the total atomic number, it's 1 plus 1 2, and even here it's 2 plus 0 2, fine, and the mass number is 2 plus 2 4, whereas here it is 3 plus 1 4. So even the mass number is preserved, and yet the actual weight of the reactants is slightly more than the actual weight of the products combined. This loss in mass is converted into energy. And here's another example which you need to remember. Deuterium is just an isotope of hydrogen. Usually hydrogen has just one proton and no neutron, so its mass number is also 1, just like the atomic number. That's called a protium. But deuterium is a little heavier hydrogen, and we also have tritium. Here it's an helium isotope, 3 2, that is 2 protons and 1 neutron, and see how this 1 neutron is also ejected out. Here a helium and hydrogen react to form a helium and a proton, that is a hydrogen atom. Understand that no electrons are involved in these reactions. These are nuclear reactions. Some more examples are these. We just have to be able to balance the atomic numbers or mass numbers on the LHS or RHS. Notice there is one exceptional equation out here, which is the equation which happens in the stars, including our sun. 4 hydrogen atoms, or rather nuclei, they fuse together to form a helium nucleus, and also they give out positron. Positron is a positive electron. That's right, it's the antimatter of electron. It's not a proton, no, it's very light. Its mass is as less as that of an electron, but an electron which is positively charged is called positron. Surprising as it may be, but that's the higher physics which you'll study in college level. So this equation is not very important from a syllabus point of view, but we should know that this is a reaction which happens in the sun, and it gives neutrino particles which are extremely small, even smaller than electrons, and it gives energy, and this is the energy which we get, and we are alive because of the solar energy which we get here. But the thing is, such nuclear fusion reactions can take place only at very high temperature, around 10 raised to 7 Kelvin. That's a 10 million Kelvin. That's incredibly hot. That's the temperature in the core of the sun, which can be achieved only under very high pressure. This is important because only at such high temperature and pressure can these nuclei fuse together. See, if you understand, this is actually a proton. All of these are protons. Positive charges repel each other. As they come closer to each other, the repulsive force is immense. So we need something even greater, even more powerful to force them to fuse together, and that is only possible at such a high temperature. And that's why replicating such equations, such reactions on Earth is extremely difficult. Achieving such high pressures and temperature is not feasible right now. It's not practical, it's very dangerous. But if we could one day have nuclear power plants running on nuclear fusion rather than fission, that would solve a lot of our energy problems, because then we'll have unlimited supply of energy. We've got a lot of hydrogen available here. Our oceans have a lot of hydrogen. We can get it by electrolysis. We can get the deuterium or the protium from it. And the energy released is so much that it could satisfy the energy needs of all the nations. We won't have to ever use fossil fuels ever again, if only we could achieve nuclear fusion practically on Earth. Yes, such reactions can be used to manufacture hydrogen bombs as well, which is much more disastrous compared to nuclear bombs based on nuclear fission, but that's a destructive use of it. Now, one uranium atom gives only 190 mega electron volt, whereas one hydrogen, a few hydrogen atoms in one reaction, they give just 24.7 mega electron volt. So you may think that nuclear fusion gives less energy, but understand that uranium is quite a heavy element and hydrogen is a very light element. It's the lightest element. So if you talk about the total mass, a fixed mass, let's say 1 kg of uranium and 1 kg of hydrogen, fixed mass, equal mass. And now if we calculate the total energy released by uranium's fission and the total energy released by 1 kg of hydrogen's fusion, then definitely fusion produces more energy. That's one advantage of fusion. Another advantage is that the hydrogen which we use for fusing or the helium produced after nuclear fusion, they are all not radioactive. In case of fission, uranium and the products like barium, they are radioactive. So disposing them is quite difficult because the harmful radiations can be dangerous. But here, there are no harmful radiations produced. And the third advantage, as I've already said, is that the fusionable substance, that is deuterium from seawater, is found in abundance on Earth. But there are some disadvantages also of nuclear fusion. The disadvantage is point number 2 and 7. Point number 2, well, this reaction is possible only at very high temperature and very high pressure, unlike nuclear fission, which does not require such conditions. And another disadvantage is that it cannot be controlled. We don't know yet how to control it. We have even requested Tony Stark to try to build the fusion reactors, but he hasn't been successful yet. On the other hand, nuclear fission can be controlled, so that is why it is being used on a large scale. That's the future. What differences? Well, the definition, of course, heavy nucleus into light fragments, and here light nuclei into a heavy nucleus. And finally, this can be used to build a nuclear bomb, whereas this is used for a hydrogen bomb. But in both cases, one thing is similar: energy is released because of loss in mass as per Einstein's equation. The solved examples are cancelled. There are no numericals for this part, so cancel the numericals here as well. And practice all the equations of this chapter.